For millennia, humanity has been captivated by gold. It is a symbol of wealth, of power, of beauty. We have fought wars over it, explored continents for it, and adorned our greatest achievements with its luster. Yet the vast majority of our planet's gold is completely beyond our reach. It is locked away, thousands of kilometers beneath our feet, in the very heart of the Earth. This incredible treasure trove, vast enough to coat the entire surface of our world in a thick, shimmering layer, has always been thought to be a one-way deposit. But what if that story is changing? A new discovery suggests just that, hinting at a remarkable journey of gold from the core to the crust. This is a story of immense pressures and unimaginable temperatures. It is a tale of a planet that is far from static, a dynamic and ever-changing world. To understand this incredible story, we must first travel back in time. We go back over 4.5 billion years to the birth of our solar system. The early Earth was not the blue marble we know today. It was a chaotic, molten ball of rock and metal, constantly bombarded by asteroids and comets. In this fiery furnace, the elements that make up our world began to separate. The heavier elements, those with greater mass and density, were pulled inexorably towards the center by the force of gravity. These are what we call siderophiles, or iron-loving elements. They have a chemical affinity for iron, and as molten iron sank to form the planet's core, it dragged almost all of the world's precious metals down with it. So efficient, in fact, that scientists calculate there is enough gold in the core to cover the entire land surface of Earth, in a layer 4 meters deep. This is why gold is so rare on the surface. The gold we mine today, the gold in our jewelry and our electronics, is thought to have arrived later. It was delivered by a relentless bombardment of asteroids during a period known as the Late Heavy Bombardment, long after the core had formed and the planet's surface had started to cool. This has been the accepted story for decades. It explained the presence of gold in the crust while respecting the fundamental physics of planetary formation. It was a neat and tidy explanation. Our planet is structured like an onion with several distinct layers. At the very center lies the inner core. It is a solid ball of iron and nickel, about the size of the moon. The pressure here is astronomical, over 3.5 million times the pressure at sea level. This immense pressure is what keeps the inner core solid, despite temperatures hotter than the surface of the sun, reaching an estimated 6,000 degrees Celsius. Surrounding this solid sphere is the liquid outer core. This layer is also made of molten iron and nickel, and it is in constant churning motion. The flow of this conductive fluid is what generates our planet's magnetic shield, which protects us from harmful solar radiation. Without the outer core, life on Earth would be impossible. This next layer is the mantle. The mantle is the thickest section of the Earth, making up about 84% of our planet's volume. It is not a liquid, as is commonly thought, but a solid that behaves like a very, very thick, slow-moving fluid over geological timescales. The boundary between the core and the mantle, known as the core-mantle boundary or CMB, is the most dramatic frontier inside our planet. It is a region where the searing liquid metal of the outer core, at over 4,000 degrees Celsius, meets the cooler solid rock of the lower mantle. This is where our story of leaking gold truly begins. So how does gold, an element that loves to be dissolved in iron, make its great escape from the core? The secret lies in the unique and extreme conditions at the core-mantle boundary. Here, the intense heat from the liquid outer core cooks the base of the rocky mantle. This process is not gentle. It creates profound chemical changes in the mantle rock. Over millions of years, this interaction can cause a strange phenomenon. The composition of the mantle rock at this boundary can be altered, making it capable of pulling certain elements out of the core's liquid iron. Think of it like a chemical sponge. The rock at the base of the mantle, under immense heat and pressure, becomes transformed. Scientists believe that the presence of oxygen in the mantle rock changes the chemical equation. This oxygen-rich rock can essentially rust the liquid iron it touches, causing some elements, including precious metals like gold and platinum, to precipitate out of the core's solution. This is the first crucial step in the journey. The gold is no longer part of the core, it has crossed the boundary. This region becomes enriched with these heavy, core-sourced materials. It is a zone of transition, a chemical staging ground for an upward journey that will take hundreds of millions of years. The process is incredibly slow, a gradual accumulation of core materials into the lowermost parts of the Earth's mantle, forming what geologists call ultra-low velocity zones. This is not a violent leak, like water from a pipe. It is a subtle, persistent chemical migration driven by the fundamental laws of thermodynamics and chemistry under extreme conditions? Once these core-enriched pockets of rock have formed at the base of the mantle, they're ready for the next stage of their epic journey. Because they've been superheated by the core, these pockets of rock are hotter and less dense than the surrounding mantle material, and in the great slow-motion convection current of the mantle, hotter things rise. These columns are known as mantle plumes. You can think of a mantle plume as a colossal, slow-moving lava lamp for the planet. A blob of hot material detaches from the base and slowly, over tens of millions of years, travels thousands of kilometers towards the surface. As it rises, it carries with it the unique chemical signature of its origin, including the traces of gold and other materials it scavenged from the core. This is the transport mechanism, the geological highway that connects the deepest parts of our planet with the crust we live on. These plumes are the engines behind some of the most dramatic volcanic activity on Earth. When the head of a mantle plume reaches the base of the lithosphere, the rigid outer layer of the planet, it spreads out, causing immense melting. These are not your typical volcanoes found at the edge of tectonic plates. These are hotspot volcanoes which can form anywhere, even in the middle of a tectonic plate, punching a hole straight through it. The most famous example of a hotspot track is the Hawaiian Emperor Seamount Chain. The island of Hawaii sits directly above an active mantle plume right now. It is in the lava from these specific types of volcanoes that scientists believed they might find the evidence they were looking for: the chemical fingerprints of the Earth's core. If a mantle plume is indeed a highway from the core, then the lava it produces should contain the evidence. The volcanic rocks formed from this lava should be different from other rocks. They should bear a chemical signature, a sort of geological DNA, that traces their origin back to the core mantle boundary. Scientists focused their attention on a very specific element: tungsten. Tungsten, like gold, is a siderophile, an iron-loving element that should predominantly reside in the core. However, tungsten has several isotopes, which are atoms of the same element with slightly different masses. Critically, the isotopic ratio of tungsten in the Earth's core is thought to be different from the ratio found in the mantle. This is because another element, hafnium, which is not found in the core, slowly decays into a specific isotope of tungsten over billions of years. Therefore, if rocks on the surface showed a tungsten isotope ratio that was shifted towards the core's signature, it would be a smoking gun. The Hawaiian Islands, being the product of one of the most powerful and long-lived mantle plumes on the planet, were the perfect laboratory for this investigation. The dark basaltic rocks that make up the islands are the solidified form of magma that originated deep within the mantle. Each eruption brings fresh samples from below, offering a snapshot of the plume's composition. By studying these rocks, especially the older ones, scientists could piece together the history of the plume and search for any variations that might point to a contribution from the planet's metallic heart. The groundbreaking research was led by a team of geochemists who dedicated years to this puzzle. Their work, published in the journal Geochemical Perspectives Letters, represents a monumental effort in analytical science. The team needed to measure the tungsten isotopic ratios with extraordinary accuracy. The expected difference between mantle rock and core-influenced rock was minuscule, parts per million. It required state-of-the-art mass spectrometers and incredibly careful sample preparation to eliminate any possibility of contamination. After analyzing countless samples of volcanic rock from Hawaii and the Samoa hotspots, the team found what they were looking for. The results were stunning. The rocks showed a small but significant shift in their tungsten isotope ratios. They were slightly different from typical mantle rocks. Crucially, they were shifted in the exact direction you would expect if they contained a small amount of material from the Earth's core. This was the chemical fingerprint they had been searching for, the evidence that the core mantle boundary is not a perfect seal. It was the first direct proof that the core is, in fact, leaking. The scientists had successfully traced a pathway, a chemical trail, that stretched for nearly 3,000 kilometers from the edge of the core to the volcanoes of the Pacific. This discovery was a watershed moment in geology. It confirmed a theory that had been debated for decades but had lacked definitive proof. The work of these scientific detectives gave us a new lens through which to view our world, revealing it to be a more integrated and dynamic system than we had ever realized. This discovery does not mean we should start prospecting for gold in Hawaii. The amount of core material reaching the surface is incredibly tiny. The leak is more of a slow chemical seepage that has been occurring over geological eons. The true value of this finding is not in the metal itself, but in what it tells us about our planet. It forces us to rethink the relationships between Earth's different layers. The core, mantle, and crust are not just separate components stacked on top of each other, they are part of a single interacting system that exchanges material and energy over vast timescales. This new understanding has profound implications for many areas of geology. It could help us better understand the nature of mantle plumes and hotspot volcanism. It also provides a new tool for mapping the deep Earth. By studying the chemistry of hotspot lavas around the world, we may be able to identify other areas where the core is leaking and create a map of the core mantle boundary's most active regions. Furthermore, this has implications for our understanding of how the Earth has evolved. The exchange of material between the core and mantle may have been more vigorous in the planet's past when it was hotter. Ultimately, this finding enriches our perception of the Earth. It transforms our view of the planet from a static ball of rock to a living, breathing entity with a circulation system that connects its deepest heart to its outer skin. The fact that we can stand on a volcanic rock in Hawaii and hold a piece of evidence that has traveled from the edge of the core is a testament to the dynamic nature of our world. The story of the leaking core is a powerful reminder that our planet is a place of constant motion and change. It is not a finished object but a work in progress, an active and evolving system. Every volcano that erupts, every earthquake that shakes the ground, is a message from the deep, a sign of the immense forces at work within. With each new technological advance, we peer deeper and with greater clarity. We are developing new ways to map the mantle using seismic waves, new techniques to analyze the chemistry of rocks with incredible precision, and new models to simulate the complex physics of the core. Who knows what we will find next? Perhaps there are other, even more surprising exchanges of material happening deep within the planet, influencing our world in ways we cannot yet imagine. This quest for knowledge is fundamental to our nature. We look to the stars and wonder about other worlds, but there is a universe of mystery right here beneath our own feet. Understanding our planet's inner workings is not just an academic exercise, it is crucial for understanding everything from natural hazards like earthquakes and volcanoes, to the long-term cycles that govern our climate and the distribution of resources. And so, the next time you see a piece of gold jewelry or a dark volcanic rock, perhaps you will see it differently. See it not just as a metal or a stone, but as the end product of an extraordinary journey. A journey that began in the fiery heart of a young planet, spent billions of years locked in a metallic core, and then traveled for millions of years on a plume of rising rock to finally reach the surface. It is a tangible piece of our planet's deep history, a glimmer of the vast, hidden wonders that still lie waiting to be discovered in the heart of our living world.